Welcome to our introduction to thermal chemistry and enthalpy. Thermal chemistry is the study of heat energy changes that occur during chemical reactions. Enthalpy, represented by the symbol H, is a measure of the total heat content of a chemical system. Enthalpy change, or delta H, refers to the heat transferred during a chemical reaction that occurs at constant pressure. The enthalpy change can be calculated using the equation delta H equals the enthalpy of products minus the enthalpy of reactants. Let's explore the two main types of reactions based on their enthalpy changes. In exothermic reactions, heat is released to the surroundings. These reactions have a negative enthalpy change, meaning the products have less energy than the reactants. In contrast, endothermic reactions absorb heat from the surroundings. These have a positive enthalpy change, meaning the products have more energy than the reactants. Common examples of exothermic reactions include combustion processes, while photosynthesis is a well-known endothermic reaction. To summarize, enthalpy change is a fundamental concept in thermal chemistry that helps us understand and classify reactions based on their heat transfer. Remember these key points. Delta H measures heat transfer at constant pressure. Exothermic reactions have a negative delta H and release heat. Endothermic reactions have a positive delta H and absorb heat. Entropy is a measure of molecular disorder or randomness in a chemical system. We can visualize entropy by comparing ordered and disordered arrangements of particles. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. As time progresses, molecular systems naturally move from ordered to more disordered states, increasing their entropy. Now, let's explore the factors that determine if a reaction leads to increased entropy. First, changes in physical states. As matter transitions from solid to liquid to gas, entropy increases. This is because particles gain more freedom of movement, increasing the system's disorder. The second factor is the change in the number of gas molecules. When a reaction increases the number of gas molecules, entropy increases. For example, when one gas molecule splits into two, the system has more possible arrangements, increasing entropy. The third factor is molecular complexity. More complex molecules typically have higher entropy. Complex molecules can adopt more configurations and energy states, increasing the disorder in the system. Let's examine how we quantify entropy change in chemical reactions. The change in entropy, delta S, equals the entropy of products minus the entropy of reactants. A positive delta S means entropy has increased, indicating greater disorder in the system. Conversely, a negative delta S means entropy has decreased, resulting in a more ordered system. To conclude, let's visualize how entropy relates to molecular movement by examining phase transitions. In a solid, particles are locked in a rigid structure with minimal movement, resulting in low entropy. When a solid melts into a liquid, particles gain more freedom to move, increasing the system's entropy. Finally, in the gas phase, particles move freely throughout their container, maximizing disorder and entropy. The greater the molecular freedom, the higher the entropy. This fundamental relationship helps us predict the direction of spontaneous processes in nature. In thermodynamics, Gibbs free energy helps us determine whether a chemical reaction will occur spontaneously. Gibbs free energy, represented by G, is the thermodynamic potential that combines enthalpy and entropy to determine whether a reaction occurs spontaneously. The fundamental equation for Gibbs free energy is delta G equals delta H minus T delta S, where delta G is the change in Gibbs free energy, delta H is the change in enthalpy, T is the temperature in Kelvin, and delta S is the change in entropy. The sign of delta G determines whether a reaction occurs spontaneously. When delta G is negative, the reaction is spontaneous. When delta G is positive, the reaction is non-spontaneous. And when delta G equals 0, the system is at equilibrium. In a spontaneous reaction, the Gibbs free energy decreases, resulting in a negative delta G. Energy flows downhill. In a non-spontaneous reaction, energy must be added to the system, resulting in a positive delta G. The reaction would only occur with external energy input. temperature plays a crucial role in determining spontaneity. Let's examine how temperature affects the T delta S term in our equation. There are four possible combinations of enthalpy and entropy changes. When both enthalpy is negative and entropy is positive, the reaction is always spontaneous at all temperatures. When enthalpy is positive and entropy is negative, the reaction is never spontaneous. When enthalpy is negative but entropy is also negative, the reaction is spontaneous only at low temperatures. And when enthalpy is positive but entropy is also positive, the reaction becomes spontaneous at high temperatures. Let's visualize these combinations in a quadrant diagram, showing how enthalpy and entropy together determine spontaneity. The quadrant diagram shows the four possible combinations of enthalpy and entropy changes. The upper left quadrant, where delta H is negative and delta S is positive, shows reactions that are always spontaneous. The lower right quadrant, where delta H is positive and delta S is negative, shows reactions that are never spontaneous. The other two quadrants show temperature-dependent spontaneity. When delta G equals 0, the system is at chemical equilibrium. At this point, the forward and reverse reactions occur at equal rates. At equilibrium, the free energy of the system is minimized. The forward reaction converts reactants to products at the same rate as the reverse reaction converts products back to reactants. The system appears macroscopically unchanged, even though reactions continue at the molecular level. To summarize, Gibbs free energy combines the effects of enthalpy and entropy to determine reaction spontaneity. A negative delta G indicates a spontaneous process. Temperature can determine whether enthalpy or entropy dominates. And when delta G equals 0, the system is at equilibrium.